Welcome to the deep dive. Today, we are strapping in for something that sits right at that intersection of, well, geology and maybe a little bit of existential dread.
Just a little.
We're talking about the Yellowstone supervolcano. We've gone through a stack of sources on this, and they all seem to agree on one thing. This is an event that could, and this is a quote, change life on Earth.
And that phrase, change life on Earth, that's really the key here. For this deep dive, our goal is to get past the simple question of if it could happen and really dig into what the sources say the actual consequences would be.
The mechanics of it.
Exactly. What does it look like? What are the domino effects? We're pulling out the core knowledge you need to really grasp the scale of this thing.
Right. You want the aha moments, the facts that really explain why this is such a massive potential threat. So let's jump right in. Okay, let's start with the big one. We always hear the term supervolcano. It sounds scary, but what really makes Yellowstone different? I mean, what's the tangible difference between this and, say, an eruption like Mount St. Helens?
The difference is it's monumental. The sources are very clear on this. It's called a supervolcano because its potential eruption is thousands of times stronger than a typical volcano.
Thousands of times.
Yeah, and we're not talking about a simple linear increase in power here. It's an exponential jump.
So it's not just a bigger mountain blowing its top. Is there like an index for this?
Yeah.
A way to measure it?
There is. It's the Volcanic Explosivity Index, the VEI. Most big eruptions we hear about might be a VEI 5, maybe a 6.
Okay.
The last major Yellowstone eruption, that's estimated at a VEI 8. That's the highest possible level. It's not just about how high the ash goes, it's about the sheer volume of material, magma, rock, ash that's ejected over hours, maybe even days.
So when you take that scale into account, what's the big takeaway from the sources?
The implication is that if this were to happen, it would be, and I'm quoting here, the biggest event in modern human history.
The biggest event.
It would literally rewrite maps. It would redefine geological time for us as a species. And understanding that scale, that's really step one.
Okay, so let's move from the what to the how. We've established the power. What do the sources, the models say about the eruption itself? The launch. How high does all this stuff actually go?
This is where the physics get, kind of mind-bending. The sources say the eruption could blast ash and debris up to 40 kilometers high into the atmosphere.
30 to 40 kilometers, that's not just high, that's getting into the stratosphere, right? Above where our weather happens.
Precisely. You're punching through all the local weather systems and injecting this material directly into the jet streams that circle the globe.
You're basically creating a planetary chimney.
That's a great way to put it. And once it's up there, it spreads fast. But before it goes global, It has to come down. And the regional impact is, well, the sources describe it as immediate and catastrophic.
Right, the ground zero effect. What part of the country are we talking about? Where's the immediate disaster zone?
The focus is squarely on North America. The sources paint this really dire picture where the middle of America, think the Rocky Mountain states, the Midwest, would disappear completely under several meters of ash.
Disappear. We're not talking about a dusting of ash that you can shovel off your car.
No. We're talking about burying entire cities, rendering huge parts of the country completely uninhabitable for a very long time.
And a landscape buried like that, I mean, that's an immediate total collapse of everything. It's not just the ash, it's the end of modern life in that zone.
Absolutely. So sources list these immediate domino effects. Think about transportation. All airports would just shut down, disabled, not just by the weight, but the ash itself is. It's incredibly abrasive. It would destroy jet engines, make runways useless.
And what about the most basic thing, our food supply?
That's maybe the most critical short-term failure. Agriculture would just collapse.
Yeah.
In the breadbasket of America, the fields would be buried, the sky would go dark. That's an instant end to the growing season, and that disruption would ripple out far beyond the blast zone.
So, regional paralysis. That's the immediate effect. Now let's go global, because that's where the supervolcano really comes into play. How fast does this stuff spread?
Right. This is where it shifts from a continental catastrophe to a planetary crisis. The scientific models in the sources are pretty clear. The ash plume, once it's in that jet stream, could reach places as far away as the Middle East and Europe within just 2 weeks.
2 weeks. 14 days to cross continents. That puts the entire world on notice, basically instantly. But the ash isn't the real long-term killer, is it? The sources point to something else, this volcanic winter.
That's the crux of it, yes. And this is a really important distinction the material makes. The primary cooling agent isn't the ash. Ash is heavy, it settles out of the atmosphere in weeks, maybe a few months.
So what is it then?
It's the gas, specifically the massive quantities of sulfur dioxide that get blasted up there with the ash.
And what does sulfur dioxide do when it hits the stratosphere?
It reacts with water vapor and forms these tiny, tiny reflective particles, sulfate aerosols. And the key thing here is they're incredibly small and light. They don't just fall back to Earth. They can stay suspended up there for years.
So you've suddenly coated the upper atmosphere in this fine layer of reflective material, like a mirror.
Exactly like a planetary mirror. These particles reflect incoming sunlight back into space. The sources say they essentially prevent the sun's heat from reaching the surface. You're basically turning down the thermostat for the entire planet.
That's a much bigger threat than the initial explosion. So what's the result? How long does this dark, cold period last?
The models project a volcanic winter that could go on for months or even several years, and that would cause the Earth's average temperature to drop, well, dangerously low.
Low enough to disrupt growing seasons everywhere, right? Not just in the U.S.
Precisely. You could see growing seasons fail across the entire northern hemisphere. It's a devastating hit to global food security. So you have this double punch threat. Regional burial by ash, and a global famine from the climate change.
Okay, it's a scientifically grounded and pretty bleak picture.
It is. But we have to stress, this is the worst case, low probability scenario the sources describe. And now we have to pivot to what the sources say about right now, the present reality.
That's the critical question, isn't it? After all that, can we sleep tonight? What do the sources say about how we're actually monitoring this thing?
And that's the reassuring part. The material is very firm on this. Yellowstone is one of the most intensely monitored geological spots on the entire planet. Scientists are watching it 24 hours a day, 7 days a week.
With what, though? What are they actually looking for? I know the sources mentioned three main things: small earthquakes, temperature changes, and gases.
Right, but they're not just looking for one of them. They're looking for all three happening together. That's the key. For earthquakes, they're tracking these clusters of small quakes. They call them swarms.
Swarms?
Yeah, and crucially, they're looking to see if those swarms are happening at the same time. The ground itself is starting to bulge, to lift up. That combination means magma or other fluids are moving around down there.
Okay, so swarms plus ground uplift is one warning sign. What about the heat?
They monitor that with sensors in the ground and also with satellites. They're looking for significant, sustained temperature increases in the ground and in the hot springs. A big jump would suggest magma is rising closer to the surface.
And the third one, the gases. That seems like the most direct measurement, almost like taking the volcano's pulse.
It really is. They're constantly analyzing the mix of gases coming out of the ground. Normally, it's mostly steam. A huge red flag would be a sudden spike in magmatic gases like sulfur dioxide. If you see that, plus the earthquake swarms, plus the ground swelling, that's when the alarm bells really start going off.
It's that combination of all three. That robust surveillance it's the big difference between now and past eruptions. So after all this, what is the final verdict? The probability check.
The final assessment across all the sources is consistent. The current probability of a major eruption is, quote, very low. The potential impact is catastrophic, yes, but the likelihood, right now, is tiny. The system is active, but it appears to be stable.
So, incredibly high impact, but incredibly low probability. That really sums it up. It's scary stuff, but getting this factual, detailed look at the mechanics, that's what makes this a worthwhile deep dive.
I agree. We know the key isn't just the ash, it's the sulfate aerosols causing a volcanic winter. We know the immediate threat is the complete burial of the U.S. heartland. This context is what makes the surveillance so important.
It's that tension, right, between the low probability and the absolute nature of the risk.
Exactly. And that actually brings up a final thought for you, the listener, to mull over. We know from the sources that this event would be the biggest event in modern human history. We also know it's monitor 247, and the probability is very low.
Right.
So if we have absolute knowledge of an absolute civilization-ending risk, how should our societies actually integrate that knowledge into long-term planning? I don't just mean for the region, but for global economic and agricultural strategy.
When the scientific risk is marginal, but the outcome is planetary collapse.
Yeah.
What's the right level of preparedness? That is a huge question, and it goes way beyond geology, something to think about long after this deep dive is over.
Absolutely.
Thanks for joining us for this deep dive into the world's most famous supervolcano. We'll catch you next time.